Welcome. In this lecture, the methods available to calculate the beam slopes and deflections at any cross-section along a beam's length are highlighted. Methods to calculate the slope and deflection at any cross-section along a beam's length include double integration method, Macaulay's method, also known as method of singularity or half-range functions, area moment method, conjugate beam method, and unit load method. We shall specifically emphasize on the double integration method to start with and shall primarily rely on the extension of the double integration method, that is, Macaulay's method, in this course. Other methods mentioned here are outside the scope of present discussion. Before we try to understand the double integration method to calculate a beam's slope and deflection, let's first go through the differential equation of an elastic curve. Assumptions made to derive the differential equation of an elastic curve include: axis of the beam is horizontal before loading. Deflection due to shear is negligible. Material of the beam is homogeneous, isotropic, and obeys Hooke's law. The modulus of elasticity is the same in compression as well as in tension. Plane sections remain plane before and after bending. The value of the deflection and hence slope at any cross-section is very small compared to the length of the beam. Without going into the details of the derivation, the curvature of the beam at any cross-section, namely the inverse of the radius of curvature or 1 over r, is found equal to d2y over dx square divided by 1 plus dy over dx squared to the power of 3 over 2. In any practical case of bending of beams, the slope, that is dy over dx, is very small because the curve is almost flat due to greater length corresponding to the deformations, hence the square of the slope can be ignored. So the curvature can be equated to d2y over dx square. From the flexure equation, m over I equals E over r, we have 1 over r equals m over the flexural rigidity EI, which is equal to d2y over dx square. Hence, m equals EI times d2y over dx square. This is the differential equation of an elastic curve for beam deflection and shall be the starting point to derive the slope and deflection at any cross-section along a beam's length for both the double integration method and the Macaulay's method. Note that the distance x is taken positive when measured from left to right, and the vertical distance or deflection y is taken positive when measured above the undeformed neutral axis and is negative when measured below the undeformed axis of the beam. Also, the angle of the slope is measured in radians. Let's now understand in brief the double integration method for finding beam slopes and deflections. From the differential equation of an elastic curve, m at a section at a distance x from the reference equals EI times d2y over dx square. We integrate it twice to get the equations for slope and deflection with 1 and 2 constants of integration respectively for slope and deflection. The two constants of integration are found out by inserting two boundary conditions, either from known values of slope and or deflection at certain points along the beam length, especially at the supports. The method of double integration is convenient only in simple loading cases, where the number of loads acting on the beam are minimal. In the general case of loading, where several loads are acting, the bending moment expression for each of the different regions separated by loads is different, and hence two constants of integration are added to every region. Then the method of double integration will become extremely lengthy and laborious due to the inclusion of a large number of unknown constants to be found out. Therefore, it is not generally used. In such a general case, we resort to Macaulay's method, for which the number of unknown constants, that is 2 in this case, is independent of the number of loads acting on the beam, and only one bending moment expression is written for the entire beam. For Macaulay's method, or the method of singularity or half-range functions, we make use of a half-range function defined by function of x minus a to the power of n in pointed brackets is equal to either x minus a to the power of n in regular curved brackets if the argument x minus a is positive, that is x is greater than a, or the function of x minus a is simply taken equal to 0 if the argument x minus a is negative or equal to 0, that is, if x is less than or equal to a. It is to be noted that the integration of the argument in pointed brackets is to be performed as a whole and not after expanding it using usual mathematical methods. For example, integration of x minus 2 square is to be taken as x minus 2 to the power of 3 over 3 and not the integration of x square minus 4 times x plus 4. Also, another point to remember during analysis of beams by Macaulay's method is the representation of an applied bending moment at some location along a beam's length in the form of half-range functions. If a moment m acts at a location at a distance of a from some reference position along the beam's length, then the moment expression has to be represented in half-range form as m times x minus a in pointed brackets to the power of 0. It may seem at this stage that this is unnecessary. Later, you will understand that this is important to be done to give us the freedom to deselect the role of applied bending moment m in calculating the slope and deflection in the part of the beam to the left of the applied moment m. It is also to be understood that Macaulay's method of finding slope and deflection enables it to be implemented in computer programming. Having understood the differential equation of an inelastic curve, we shall seek to understand the mathematical relation between rate of loading, shear force, bending moment, slope and deflection for any cross-section along a beam's length in the next lecture.